Hello, and welcome to our lecture on logarithmic functions. Last time we studied the exponential function, and we noticed that it was a one-to-one function, and hence it has an inverse. And that inverse will be the logarithmic function. So let's step back and remind ourselves what the exponential function looks like. Here's how it's defined. F of x is equal to a to the x, where a is a positive real number and a is not equal to 1. The base is never equal to 1. And that exponential function passes the horizontal line test. You'll remember what the graph of 2 to the x looks like. Here it is. 2 to the x passes the horizontal line test. So it will have an inverse. And in fact, you can already guess what the graph of that inverse looks like, can't you? Remember how you graph the inverse of a one-to-one function? It's the mirror image across the line y equals x. So keep that in mind as we keep going. This exponential function has an inverse, and this will be called the logarithmic function. Here's the technical definition of the logarithmic function. And I'm the first to say up front, it's kind of scary the first time you see this. If you've never studied logarithms before, this kind of looks like, whoa, this is pretty hard. But we'll do some examples, and then fortunately the workbook has more examples and exercises that you can try on your own. So here we go. For x greater than 0, in other words, the domain of the logarithmic function will be positive real numbers. And for a greater than 0 and not equal to 1, a is going to be the base of our logarithmic function. Here's the definition. Y equals log base a of x if and only if x equals a to the y. In other words, the logarithm function is defined in terms of the exponential function with the roles of x and y kind of flipped. So this function, f of x equal log base a of x, that's called the logarithmic function with base a. Kind of scary, I admit. Let's do some computations. Let's play with logarithms for a moment. And remember, the key is y is log of x to base a if and only if x equals a to the y. Watch the interplay of these numbers. What's the logarithm to base 2 of 32? Well, I claim it's 5, because if I go over to exponent land, 2 to the 5th equals 32. Notice that logarithms are exponents, aren't they? 2 to the 5th is 32. What's the logarithm base 3 of 1? Well, I claim it's 0 because if I transfer over to exponents, I get 3 to the 0 equals 1. How about log base 4 of 2? I claim that's a half because 4 to the 1/2 power means square root of 4, or 2. And how about log base 10 of 1,000? Well, that's equal to 3 because 10 cubed equals 1,000. So you can calculate these logarithms by converting back to an exponential problem. Let me give you some study tips about logarithms. First of all, you can't take the logarithm of 0 or the logarithm of a negative number. If you don't believe me, try it on a calculator. You'll see what happens. Logs to base 10, that's a very common type of logarithm, and in fact, they're called common logarithms. And the other kind of logarithm that is on your calculator, not only is the common logarithm key on your calculator, but there's also a key for the natural logarithm, which is the base e logarithm, and we'll come to that in a few minutes. And again, because the exponential function is one-to-one, the logarithmic function is also one-to-one, because they're inverses of each other. Good. Let's do some more properties of logarithms. And some of these properties are really quite important. I want to get them sort of on the table. For instance, log of 1 is 0 to any base, base a. The log of 1 is 0 because a to the 0 is 1. So sort of keep in mind, log of 1 is 0. Log of a to base a is 1 because a to the first power is a. So those are pretty simple. Here's a very subtle and crucial property. Log base a of a to the x can be compactified to x. Let me convince you why that's true. Well, that's the composition of two functions. And in fact, it's the composition of inverse functions. First, you do a to the x, and then afterwards, you log your result. And those are inverses, so they undo each other, and you're left with just x. That property will occur over and over again. And a different version of it is the composition the other way. A to the power log base a of x is also equal to x, because again, it's a composition, isn't it? But now you're doing log first, and afterward you're doing a to that answer, and they undo each other, and you're left with x. So keep those properties in mind. They occur quite a bit in the applications of logarithms. And of course, we said logarithm was 1-to-1, so if you ever have an expression that log of x equals log of y, both to the same base, then x will equal y. All right, let's play with logarithms. Let's play with logarithms some more examples. What's log base 5 of 5 squared? Well, this is an example of those inverse properties. 5 squared is the exponential, and then you log that result, so the answer is going to be 2. How about 7 to the power log base 7 of 14? Again, by those inverse powers, you get 14. How about log base 10 of 1? The common logarithm of 1, that's going to be, of course, 0. And what about the logarithm of 0? Undefined. You can't take the logarithm of 0. The domain of the logarithm function is x bigger than 0. Okay, let's graph the logarithm function. We already tried to guess what the graph looks like, but now we're actually going to graph it. Let's graph log base 2 of x. And here's one way to do it. You could repeat your graph of 2 to the x and then flip it across the line y equals x, because it's symmetric across that line. Here's what you get when you do that. I've drawn, first of all, the graph of 2 to the x. That's our increasing exponential function. And then next to it, you see the logarithm to base 2. Let's savor this picture for a moment. This is really an important picture. If you like tattoos, this is the one you should put on yourself. Notice, first of all, that symmetry. For instance, the exponential function touches the y-axis at 0, 1. So the logarithm touches the x-axis at 1, 0. Remember, log of 1 is 0, and that's why it crosses there. How about the horizontal asymptote of the exponential function? It was the x-axis. So what's the vertical asymptote of the logarithm function? It's the y-axis. Isn't that neat? You see this interplay between the exponential and the logarithm. Let me show you another thing about this graph. What's the domain of the exponential function? Remember, it was all real numbers. That means the range of the logarithm function is all real numbers. That graph of the logarithm goes down forever and it grows forever. Let's do the opposite. What was the range of the exponential function? It's above the x-axis, isn't it? That means the domain of the logarithm function is x greater than 0. Isn't that amazing, the interplay of these two functions? They're inverses of each other, and all the properties of inverses can be used. Okay, let me summarize some of these facts that we just talked about by looking at the graphs. The inverse of the logarithmic function is the exponential function because they're inverses of each other. The domain of the logarithmic function is the interval 0 to infinity, and it doesn't include 0, and the range is all real numbers. It has an intercept, and that's at 1, 0. The log of 1 is 0. And it has a vertical asymptote, which is the y-axis. Okay. So we've seen the logarithmic function, we've seen its graphs. Let's pause for a moment and do something a little more fun. Maybe you've heard the word Google. Who hasn't heard the word Google? What is a Google? Well, a Google is 10 to the 100th power. That's a big number. It's 1 followed by 100 zeros. Don't make me write it out. But let's take the logarithm of a googol and see what happens. What's the logarithm to base 10 of a googol? Well, it'll be log base 10 of 10 to the 100th power. And now we use those inverse properties. We have 10 to the 100th, and then we're logging it afterwards. They cancel, and we're left with just 100. Okay, let's log it again. Let's log the logarithm of a googol. Log. What do we get? Well, we get logarithm of the answer we just obtained. So it's logarithm base 10 of 100, which is 10 squared. And now again, we have that cancellation, and the answer is 2. There's a moral to this story, an important moral. If you have a big number, like a googol, and you log it, the answer is pretty small. It's just 100. And if you log it again, it's really small. It's just 2. Isn't that amazing? So logarithms reduce numbers down. They kind of take a big number and they shrink it down to a small number. And by the way, I used to use the word googolplex when I was a kid. And a student once told me what a googolplex was. I think this is right. I think a googolplex is 10 to the googol power. So it's 10 to the power 10 to the 100th. There's one of those towers of exponents again, isn't it? That's what a googolplex is. That is a big number. That number is bigger than the national debt, I'm sure. Okay. Let's talk more about graphs of logarithmic functions. We've talked about the graph of log base 10 of x or log base 2 of x, things like that. And those are flips of the exponential function. Let's take some slightly more complicated graphs. What would log base 10 of x minus 1 look like? Think about that for a moment. What would the graph look like? Well, you know what log base 10 of x looks like. That's just a normal logarithmic graph. But now it's x minus 1, so it's been shifted 1 unit to the right. 1 unit to the right. The intercept used to be at 1, 0. Log of 1 is 0. Now it's log of 2 minus 1. So 2 will be the magic intercept now. And remember, the vertical asymptote used to be the y-axis? Well, that will also shift to the right. The vertical asymptote will now be x equals 1. Here's another quick example of graphing a more complicated logarithm. What does the graph of 2 plus log base 10 of x look like? What do you think that would look like? Well, again, I'm fairly comfortable with the picture of log base 10 of x. And what does the 2 do? Well, it pushes everybody up 2 units, doesn't it? So remember, 1, 0 is on the graph of log base 10 of x. That's the intercept. So that point 1, 0 gets motored up 2 units. So that intercept, which used to be at 1, 0, is now at 1, 2. It's been moved up to the point 1, 2. Okay, it's a shifted logarithm, a vertical shift of the logarithm function. So where did these logarithms come from? Who invented them? And what are they good for? Well, we'll see what they're good for in many, many lectures. But let's talk a little bit about the history. Napier, a Scottish mathematician, and Just Bourgi, a Swiss mathematician, independently developed logarithms in the early 1600s. Napier published a book in 1614 called, and I quote, "A Description of the Marvelous Rule of Logarithms." And Briggs, later on in 1624, began to show how logarithms to base 10 can be used as a computational device. In fact, they were first invented for computations. We'll learn in the next lecture that logarithms can convert products to sums in a very convenient way. And that's the basis of a device that you might have heard about, maybe your grandfather told you about it, called the slide rule. And when I was a student, back in college at Stanford, in 1964 to 68, we all walked around campus with slide rules. because we didn't have calculators back there. And we did many of our computations in chemistry classes and physics classes using slide rules. And a slide rule is based on properties of logarithms. It's an amazing device. Now, the history of logarithms started off with base 10 for computations. Later on, the base e came into play, and that's the natural logarithmic function that we'll talk about now. So, what is the natural logarithmic function? Well, the only difference now is the base is chosen to be our magic number e. Remember, we had log base 2, log base 10. Well, now it's going to be log base e. It's the mirror image of e to the x. That's the logarithm to base e. So, technically speaking, here's the definition. X is bigger than 0. The domain is x bigger than 0. And y equals the natural log of x. And you write this as ln of x. That's the notation that we use, ln of x. That means log base e of x. And y equals log x is equivalent to saying x equals e to the y. That's that definition using the exponential function. This is the natural logarithmic function. If you look at your calculator, you'll see a button that's labeled ln. That's the natural logarithm. And on your calculator, you'll have, again, 2 logarithm buttons. Log base 10, which is sometimes labeled log, and then the natural logarithmic function, ln. Let's do some properties. Let's play with this new natural logarithmic function. Well, these properties will be very similar to what we did for an arbitrary base. What's the natural log of 1? Well, it's 0 because e to the 0 is 1. The log of 1 is always 0. What's the log of e? Well, that's 1 because e to the 1 equals e. E to the first power is itself, e. Okay, let's use now some of these composition properties. What's the logarithm of e to the power x? Notice it's a composition. First we're doing e to the x, and then we're logging the result. They undo each other, and you're left with just x. And the other way around, e to the power log x is equal to x. And finally, we have this one-to-one property. If the natural log of x equals the natural log of y, then of course x equals y. Let's do some practice computations. Let's calculate some natural logarithms. What's the natural logarithm of 1 over e? Uh-oh. Well, 1 over e is e to the minus 1 power, isn't it? And now we have that property that the log and the exponential are inverses, and so the answer is just minus 1. How about e to the power log 5? Again, by those inverse properties, the answer is 5. So here's a nice problem. What's 4 times log of 1? 4 times log 1. That's 4 times 0, or 0. And by the way, let me pause here about being a math instructor. I'll have students that'll be doing a math problem in some course, and they'll turn in the answer 4 log 1. They don't simplify. They don't say, oh, that's equal to 0. How should I grade that? Think about it. Are they wrong? Not really, but they didn't really simplify as much as they could. A tough question. I don't know the answer. Okay, another quick computation. 2 log e. Can you simplify that? Well, yeah, log of e is 1, so that's equal to 2 times 1, or 2, which is sure is a lot simpler than 2 log e. Okay, what's the graph of this logarithm function look like? Well, we know the answer. We've been seeing log graphs all throughout this lecture. It looks like the flip side of the exponential graph. And it looks like other logarithm graphs. It has that intercept at 1, 0, and that vertical axis, which is the y-axis. Okay, how about an example? I'd like to go back to compound interest. We talked about a couple of formulas with compound interest, and I'd like to show something called the Rule of 70. I'm not sure you've ever heard of this rule, but I think bankers know about it. So let me try to explain what it is. Before we get started, let's remind ourselves about these formulas. Okay, you've got a deposit of P dollars in a bank, and the balance after so many years is going to be given by a certain formula, and it depends on the interest rate R, the number of compounding periods per year, and that's N, and the time T. And so the amount you have in your bank account after T years is given by the formula A equals P times the quantity 1 plus R over N, all raised to the power NT. So that's compounding N times per year. And then we pointed out that if you compound more and more rapidly, continuously, every nanosecond, even faster, you get a much cleaner formula. You get the formula for continuous compound interest, A equals PE to the RT. Again, P is the amount you deposit, R is the interest rate in decimal form, and T is the time. Okay, and we've played with this formula earlier. Let's do an application called the Rule of 70, and then I'll show you why it's true. Here's what the Rule of 70 says. It says that for continuous compound interest, the time for an investment to double at R% interest is approximately 70 divided by R. And here R is not a decimal, it's just like 5% interest. It would be 70 divided by 5. So the doubling time is 70 divided by the interest rate. For instance, suppose you deposit $100 at 5%. How long will it take you to have $200, the doubling time? Well, it's 70 over 5, 14 years. Isn't that simple? Wow. The actual time, if you do the computations using those formulas, is not quite 14. It's 13.86 years approximately, but that's a good guess. It's a good approximation. My guess is bankers know this. In fact, let me say something about bankers. Only good things, of course. If I were a banker, I wouldn't compound interest yearly or monthly or weekly. I would tell my customers, if you deposit money with my bank, I will compound that money continuously, all the time. Now, most people won't understand what that means probably, but what I'll tell them is, I'm going to compound your money all the time. It's always compounding, compound, like that, just forever. And a lot of people might think, wow, my money's really going to grow fast. Well, it's not. As we saw in an earlier example, the amount of money you earn using continuous compound interest is just a little bit more than if you compound, say, 4 times a year. But as a salesperson, I think I'll get a lot of customers this way because they'll go, wow, that bank compounds a lot. Okay, back to some math. Why does the Rule of 70 work? Let's do some mathematics. Let's show why the Rule of 70 works. So if your banker ever uses it, you can say, hey, Mr. Banker, I know why this works. Remember the formula. It's the amount is PE to the RT under compound interest. And I want the amount, which started at P, to double. So it goes from P to 2P. So I want to solve the equation 2P equals PE to the RT. I want to solve that equation for T, the time. And R is given. R is some interest rate. Assume it's, say, 5% or something. Let's solve that equation for T. Here we go. First of all, we can cancel the P's, can't we? The amount deposited is irrelevant in this computation. So we have 2 equals e to the RT. Now take logarithms of both sides of that equation. The left-hand side is log 2, and the right-hand side is log e to the RT. Aha! You recognize how to simplify that? Log e to the RT, inverse properties, they cancel, and you're left with just the exponent RT. And now you can solve for t. T equals log 2 over r. So what's log 2? Punch it on your calculator. Log 2 is about 0.69. Trust me. And now our expression is 0.69 over the interest rate r in decimal form. So if you multiply both numerator and denominator by 100, you get 70 over r%, which is the rule of 70. Isn't that cool? Nice little proof, and we use properties of logarithms to get that. Okay, you be the teacher this time. You're teaching your class, students are taking a test, and a student runs up to you and says, "Professor, I'm trying to calculate a logarithm with my calculator, and it won't give me an answer. I tried to punch in log of -2, and my calculator gave me an error message. What do I do? Is my calculator broken?" How do you answer that student who tried to compute log of -2 on his or her calculator? What do you say to the student? Well, you politely say, "Don't forget that the domain of the logarithm function, and in particular the natural logarithm function, is x bigger than 0. -2 is not in the domain, so you can't calculate the log of -2. All right, so that's fine. You can answer that question. Then another student runs up to you, and this might happen, and says, "Professor, I was able to calculate log of -2 on my calculator." Panic sets in, right? Wait a minute, I didn't think that was defined. Well, this is something very interesting and beyond the scope of this course, but if you're allowed to use complex numbers, remember those complex numbers, that square root of -1 that we called I? If you're allowed to use complex numbers, then you can actually take logarithms of negative numbers. Wow. And in fact, some calculators do their arithmetic using complex numbers. And so with some calculators, you will get an answer. You won't get an error message, you'll actually get an answer. And the answer will be log 2 plus pi I. And when I first saw this, I panicked. I go, what's going on here? First of all, there's I, which is the square root of -1. And where did the pi come from? Well, it turns out that's the correct answer. If you go on and take a course called Complex Variables, which is generally a graduate course in math departments, or at least a senior level class, you'll discover how to take logarithms of negative numbers, etc. I've taught complex variables a few times, so now I'm comfortable with this. But the first time I saw it, I kind of panicked. And so if you see it, don't panic, just sort of say, oh, complex numbers, beyond the scope of this course. Okay. I hope you've enjoyed this difficult and yet interesting first exposure to the natural logarithmic function and to logarithmic functions in general. I'm the first to admit, I'll be honest, I think logarithms are difficult. I think they're difficult for me and they're difficult for lots of students. The properties like log of 1 equals 0 is often confused with log of 0. What's that? Oh, undefined. So it's hard to keep all of it straight. I suggest when you're learning about logarithms, always keep in mind that the logarithmic function is the inverse of the exponential function. And many times you can convert a logarithmic question back to an exponential question. That said, we have a few more lectures on logarithms and exponential functions coming up, where we'll see applications of these functions, how they're used all over science and engineering. So they're interesting functions, they're difficult functions, but the bottom line is they're really useful functions. So I'll see you next time when we can continue our study of the natural logarithmic function. Thank you.